First, thank Kate for this invitation. This is really my great pleasure to give a talk in front of mathematicians. Actually, I had the dream of being a mathematician since my childhood. Unfortunately, I'm now an engineer in robotics. Okay, so actually this invitation all comes from a bag of snack in the airplane. But we're going to explain this later. Okay, so today I'm going to introduce a little bit about what I'm doing in my laboratory of motion generation and analysis in the Department of Mechanical and Aerospace Engineering. And we have some mathematical problems and which I cannot solve. So I first give introduction and talk about the challenges I'm facing in path planning and also the challenges in workspace analysis of parallel robotic manipulators. Finally, it's a conclusion. This is one prototype we developed in my laboratory. It is for generate unlimited and spherical motion with 4 robotic arms and connect to it. The idea is that this might be able to use as a flight simulator. Say, imagine that the central ball is a cockpit and people sitting inside. This ball can be rotated and unlimitedly by the 4 robotic arms connect to it. And another project, we developed Monash episodic parallel manipulator for force feedback system. It has 6 degrees freedom. And we developed this new concept, and the feature is that its motor is mounted on the ground. And so that it can generate relatively large and force and torque and rendering, and for the communication with virtual environment. And this is another project we developed, and that is for robotic surgery. And we invented a special linkage in such a way that this mechanism will only generate a pivot point and without any physical joint there. So that currently has a provisional patent on it. Okay, so that is some project in my lab. And my first problem is about path planning. Okay, so probably you know that path planning in robotics is a very fundamental problem. And basically, you have a workspace, and you want the robot to walk from one position to another position, and to avoid all these obstacles. So how can this robot do it? There are different methods. Okay, the application is enormous. It is almost everywhere, and in the industry robots, and the domestic robots, and UAV, and etc. And so current method has been classified typically in deterministic method and probabilistic method, and also the combination of these two. So, but we are thinking that can we create a more efficient method? So in the past few years, and I developed this concept that is called distorted configuration space. Okay, so there's another thing that just before entering this, coming to this building, I thought that I'm going to facing a lot of mathematicians. I look at my equations, they're really ugly. So in order not to hurt your eyes, I deleted all the equations in my slides. So this distorted and configuration space is like this. So we have workspace, for example, like this. So it is C-shaped. It is just a very standard problem. You want to find a path between any two blocks. So the idea is that, and can we distort this obstacle? Just like, actually, I borrowed this idea from black hole, and you shrink it to a single dimensionless geometric point, and by shrink this obstacle into a single point, and actually this space actually distorted. But once it is distorted, there is no more obstacle anymore. So, and I can pick up any point, any two cells, and just draw a straight line. There is a path. And then I just map it back to the original space. So I create a path here. So it seems working pretty well. So we tried different examples. Oops, okay. So this is more complicated and workspace. And this is original obstacles. One distort these obstacles into points. And the workspace is distorted in this and the new space. And draw a straight line and map it back. I can find the path. And this is another case, and in three-dimensional space. And also, we can apply this to robotic manipulator. And with the three joints, 3 degrees freedom, theta 1, theta 2, theta 3. And I actually put one obstacle here, one obstacle here, one obstacle here. So then, and these obstacles is mapped into some strange shapes and in this configuration space. Then I compress it or distort this space. Then create this I would call obstacle-free configuration space. So then the path planning was conducted correctly. Okay, so, oops, more example. Yes. Okay, so now come with the challenge here. So how did I distort this? Actually, I use the basic idea of springs. So just imagine that all these lines are just the spring with a unique stiffness. Once you change all these obstacles into a physical point, a geometric point, all these springs will be, the length will be changed according to the minimum potential energy. So what is the problem? The problem is that how can we automatically and compress or deform arbitrary obstacles in this configuration space and to create a distorted space without obstacle. In previous examples, they are quite straightforward, but I create this shape to test myself and found that I can only manually do that. I can successfully do that, but I have to manually adjust this obstacle into some strings and in this three-dimensional space so that any line will not intersect with it. But is there any automatic procedure to do it? This is something I don't know. And another thing is that you probably see that in the previous example, the path is not that optical. It actually, most of the time, is very close to the obstacle. So can we find an optimal path for it in this distorted space? And furthermore, there's another problem I'm thinking is that currently I use the strategy of the springs. So that is basically minimize the potential energy and to create this space. Is there a better method and which can actually create this distorted space and more efficiently and more effectively, and also can prove that in the distorted space all the cells are convex, and we don't want some cell to be twisted or folded, and that will not work. And most importantly, we want these methods to be generic and in any high-dimensional space. So for 2-dimensional, 3-dimensional, we still can visualize, but in robotic system, we frequently encountered and 6-dimensional or 7-dimensional and configuration space, so which is completely out of imagination. So if we can develop this kind of autonomous method, automatic method, then that would be really great and beneficial. This work currently just recently be published and in robotics, and a journal in robotics. And so we have tested, and the efficiency is much higher as compared to the traditional methods. And but I would say that the limitation is quite clear. We currently can only work on relatively simple obstacles, and with a dimension less than 3 or 4. So that is the case. Okay, so the second topic I want to mention is in my research is about parallel manipulators. So parallel manipulators is a different class of robotic manipulator, which is kind of different and from the most standard industry robotic manipulator, such as our arm. Those standard robotic arm looks like our human arm. It is a serial arm, but this one is parallel. The feature, okay, so for example, this is a flight simulator and with a steward platform on the base. It has 6 actuators to drive this cockpit to control its position and orientation. So the feature is that it is very strong and it is very precise. And the other example is that you can use this kind of system to test and to create a shaking table. And this shake table can even simulate earthquake. So this is a real size building put on this platform. And so what is the problem in this area? And the workspace are very complicated. So it suffers from the serial singularity and parallel singularity. So typically we call serial singularity is that when I stretch my arm, I cannot move any further. So this is called serial singularity. It represents the boundary. And in parallel manipulator, it has such a problem as well. But the more serious problem is that the parallel singularity. The parallel singularity is that such like I hold my arm like this and moving around. And if I can only activate my joint, and this my 2 hands fixed together, actually at this position we'll lose the control. It cannot bear any load anymore if I have low activations on these joints. So this will cause, and this result is the loss of controllability, or the gain of additional degrees of freedom of motion. So this is a very serious problem. And in parallel manipulators, and we cannot even go close to this parallel singularity. So we did a lot of study has been done in this area. And previously, people think that, and here, for example, this is the workspace boundary and of the parallel singularity. And previously, people typically think that if you have 2 points here, or if you have 1 point here, 1 point here, you cannot cross this singularity because it is separated by the parallel singularity. But probably 15 years ago, and some researchers actually tested that you can go around it. You can go around it. So then it suddenly become a very interesting phenomenon in this area. So many works has been done in this area, but it is still a puzzle. And recently, our work is like this. And in order to look at this, okay, so I need to probably say something about this picture. So this is a parallel manipulator, a very simple version with 3 degrees freedom. And we only look at 2 degrees freedom here. We actually create a solution map here. This is called solution map. This solution map's function is that on these boundaries, and we can immediately identify the parallel singularity. And the idea is that how can you generate the path around this? So this one does not tell us much. Actually, this is the most dominant method and people have been using. We actually developed a new method. This is based on topology. And we actually take all the patches and separate this. And here represent 4 solutions, 2 solutions, and 0 solutions. And here, this single patch actually have 4 layers. We separate these 4 layers in this topological map, and then link them together, and automatically. And what is interesting is that, so even the workspace is so complicated, and actually it only has 2 aspects. So all 2 groups of positions, and you can basically, and any points or any position belong to either one. So in this each group, all these positions are actually connected to each other. And that is a very new result, I would say. Okay, so here just to show you one example that, and even at this single point, it has 4 solutions, and it represents and 2. Actually, we choose 2 points, and 2 points actually projected on this plane, and we can actually go back to this point by go around this, and before it is considered and impossible. But the major point is that our discovery, okay, our discovery here is that the space, in the entire workspace has only two separate groups, and in each group, and all the positions are connected to each other. You can reach from any point to another. So this is quite significant because parallel manipulators have been considered has very limited workspace because of parallel singularity. But actually, what we show is that you can reach almost everywhere, and you have two separate groups. But, and this is only observation. This is only observation so far. And we saw some people that prove and the two separate groups and in very simple and parallel manipulator. But actually, we studied quite a number of that and used this method. We found that these two connected groups do exist, but we cannot prove it. That is a fundamental mathematical problem. I don't think I can handle that. It is too complicated. Okay, so who can help us? And so basically, this is what I proposed the problems here. And to be honest, I have no idea who can help us. I can imagine that we might need some tools or in differential geometry and something apparently in optimization to optimize the paths. And the reason to think about differential geometry is that in the distorted configuration space, actually, the space is banded. And so that the metric have to be introduced and correctly. And also group theory and topology. This is what I can imagine. But of course, and there are many powerful tools in mathematics. And for sure, I believe that many people, many mathematicians can help us in this area. So basically, and that is my talk. And just one last point is that I'm currently and organize a summer school of screw theory and at Monash University in February 2017. So screw theory is actually a theory inside of Lie group theory that has a very powerful application and in kinematics and dynamics in robotics. So if anyone is interested on this, and please also let me know. Thank you very much.